Okay, so we got a list of problems we're going to work on, 3.1, 3.2. Should we just start with 1.1 and just go like kind of chronological order? Okay, let's start. We're going back in time a bit, but that's okay. We got a midterm this week, so we should. 1.1, number 15. What is 1.1, number 15?
Oh, that's my question. My bad.
You're all good.
I think I find it. It was something about CH3COH.
Okay.
Oh, it's calculate the energy associated with the reaction if you burn 34 grams of CH3COOH.
Yeah, but you were given like additional information before that too.
Oh,
What,
yeah.
what else were you told?
When 10 grams of CH3COOH is combusted in a sealed calorimeter, it releases enough energy to heat 2,000 grams of water from 23.5 Celsius to 34.3 Celsius.
Oh, interesting. Okay. So, and then in this second reaction, are we given a volume of water? Oh, you're just supposed to calculate the delta H for the reaction.
Q.
Or the Q. Okay. So essentially what we're doing here, this is kind of a cool problem. I like it. I mean, I'm tooting my own horn there, but so essentially this is kind of how calorimetry was historically used. We do some calorimetry where we burn a known amount of material in contact with a known amount of water. That allows us to figure out the delta H of reaction. Once we have the delta H of reaction, then we can burn any amount and know how much energy we would release. So we have to split this problem solving into two steps. Step 1 is we have to get the delta H of reaction. Step 2 is we have to do it for the specified amount. Step 1 first. What am I gonna write down to do this?
The combustion reaction?
I don't even need the combustion reaction.
Q is equal to MC delta T.
That's one of the Q's. What's the other half of this?
N delta H reaction?
Not just N delta H. Negative N delta H. Okay, we got to have equal and opposite. Okay, then we see what information do I have. I know I've got 2,000 grams. I know that it's 4.184. I know that it's 34.3 minus 23.5. And that's going to be equal to 10 grams. I need to know the molecular weight of acetic acid. 1632 plus 24 is 46. 50 grams? Or is it 60? Am I off by? Is it 60?
It's 60.
Ah, okay. 60 grams per mole times delta H. Forgot my negative sign. So I'm just going to leave my negative sign over here with the delta H for a moment. I don't know, that looks terrible. We'll do this. That looks close enough. Right, so there's our N delta H. We can now solve for the delta H. I'm going to put a subscript on this. This is going to be delta H of reaction. I like putting subscripts as often as possible so that way we can kind of have a sense of what the different parts are. Subscripts are there to help us. So we do 2,000. Also help calculate, make sure I don't get the numbers wrong because I'm pretty bad with calculators. 4.184 times 34.3 minus 23.5. Wow, okay. For this side, I got 90374.4. This should be in units of joules. And that's going to be equal to 10 divided by 60. Negative. Oh. 90374. Was that did I write the same number twice? Joules. I'll recheck it in just a second. 0.167 moles, delta H. I feel like I made a mistake. Is anyone calculating with me?
That's right.
Wow, okay, yeah, those are right, okay. Now I'm going to divide by the 1.67, 0.167, and I'm going to get negative 54116. Is that right? 0 joules per mole. Or I could turn that into negative 541.16 kilojoules per mole. It's a lot of energy for every mole burned. 541 kilojoules of energy. It's huge. So that would be part one. I've got my delta H of reaction. Notice this problem never asks us to actually solve for delta H of reaction, but it's a necessary step. Now, and there's a lot of different ways we could have gotten the delta H of reaction, right? This is using this was, I don't remember who was here earlier, but one of the most difficult parts is looking at the context of the problem and being like, hey, what is this trying to get me to do? What are the tools it's asking me to use? What's the context, right? You can imagine, if this problem didn't give us that 10 grams with 2,000 grams in the temperature change, I might just write down the balanced chemical equation and look up the delta H's in a table and calculate my delta H's from the table and not have to use the MC delta T at all. Even with that temperature information there, I could still say, oh, why don't I just look up the delta H of reaction for the combustion of acetic acid? Like, that's something I can look up pretty easily, or I can calculate pretty easily. But in the context of the problem, where it gives us this information, this experimental kind of information, it wants us to do it this way. And, you know, it's not like the problem wants us to do that. You have to look at any problem you're looking at in any of your classes. You know, teachers use language like I just used of like, oh, the problem wants you to do it this way. It's like, no, I want you to do it that way. I wrote the problem. I was trying to get you to do something specific. Could you do it other ways? Yeah. But I planned on you doing it this way, and if you do it other ways, you might get a different answer than me. The reason I do problems, and there's a particular reason why I do problems this way. During like the pandemic and online education, people would be able to shortcut problems really easily by just like looking it up in tables. And so I made situations where I was like, based on this experimental data, what would you calculate? And I'd have a little note in there that says, note, this is not the literature value that you could look up. It is an experimental value you must calculate from these numbers. Because I don't want you to just be like, oh, I'll just look it up. So like I do those problems with like molecular weights, like what's the experimental molecular weight of this material? Rather than like go look it up off the periodic table, you actually have to do a particular calculation to get it. So like the problems are designed to get you to do particular things. And having that awareness, like being aware of the fact that, you know, it's a problem that was created by a person, and that person wants me to do something in particular to get to an answer that should be like something we've already done in class. It's important things to think about as we're like getting ready for how we get ready for exams. Okay, now all we have to do is multiply by 34 and divide by 60, right? Now we can do part 2. So that was part 1. Part 2 to get to the final answer is just 34 divided by 60 times negative 541.16. And that should be the answer. There's a lot of other ways you could do this mathematically. Doing it in 2 steps like this is the easiest for me. 34 divided by 60 times 541.16. So, yeah, that tracks. About 300 kilojoules of energy. How are some other quirky ways you could do this? First off, what's that?
No, go ahead.
What were you gonna say?
I was gonna say I like took the ratio like 10 and 32.
The ratio method totally works. That's
Yeah.
how I just double checked it in my head afterwards. So right, I said, oh look, if it's 10 grams to get 90 kilojoules of energy, 3 times 90 is about 300. It's like 270. And it's a little bit more than that, but 34 is a little bit more than 3 times. So that totally works, right? You can do this ratio thinking. That works. Totally works. I was trying to think of other ways, but I think those are the only 2 ways that really make sense. Questions? Common mistakes on this problem: forgetting your negative sign, forgetting to convert, right? Watch your units, watch your negative signs. So that was 1.1, number 15. Let's take a look at 3.1, number 11. What is 3.1, number 11? Do you have it ready?
Yeah, consider the chemical reaction 2HCl aqueous plus K2SO3 aqueous, and then 2 KCl plus SO2 aqueous plus H2O liquid. And then you're asked to predict the delta H.
Oh, interesting. That's it? You're not asked to predict. Oh, is the SO2 aqueous or gas?
Oh, it says gas.
Okay. As I was looking at it, I was like, oh, that should be a gas. Okay. Predict the delta H. Thoughts?
I think initially I put because like there's liquid and gas in the products that the bonds are forming, and so I thought it was going to be negative delta H, but then it's an unknown value.
Yeah.
That's where I'm confused.
Okay, so it is really difficult to predict delta H from the information that's given, right? So when I'm looking at this, I'm like, okay, well, what kind of reaction is this? It's the HCl bonds have to, like, there's a bunch of bonds breaking and there's also a bunch of bonds forming, right? So from our bond enthalpy method at the very, very beginning of the quarter, we would look at this and we'd say, well, we have to keep track of all the bonds break and all the bonds that form and figure it out. And there's just like, with the information we're given, just this information, there's no way we could tell. Because I don't know the comparison of the HCl covalent bond versus the KCl ionic bond. The SO3, like that sulfite anion, SO3 2-, has a bunch of covalent bonds in it. It's like sulfur with oxygen double bonds and oxygen single bonds, versus the SO2. Like the bonds change between those two structures. The H2O, yeah, there's some new covalent bonds there, but I can't tell. I can tell it's a redox reaction. It's a reduction-oxidation reaction, because I'm going from SO3 to SO2, like the number of oxygens is changing. I'm going from H pluses to H2Os. It almost looks like an acid-base reaction, but I think it's better categorized as a redox reaction. It's kind of both acid-base and redox, if I'm being honest. Those reactions are like acid-base reactions are usually exothermic, but redox reactions, it's hard to say, right? I will also say I've never seen a reaction that goes like this, like in one big step like this. So my guess is that we'd have to do some Hess's law thing if we really want to get the delta H of the reaction. Think about individual steps. So I have a hunch it's exothermic, but I really can't tell. I really can't tell. Does that make sense?
But how do you determine that, like, it's not negative enough to say that the enthalpy is negative and then it's unknown? Like, what?
For me, what gets me about this when I'm looking at it, like, the first consideration I did was, oh, it's like an acid-base reaction or it's like a redox reaction. I would expect those to be exothermic. But it's like those two things mixed together, and I was like, oh, there's too much going on for me to say it's like an acid-base or it's like a redox, which is why I have that hunch that we need to do some Hess's law thing to really figure it out. But once I'm like, okay, it doesn't fit easily into one of my categories where I have a good hunch, then I have to start thinking about what bonds are breaking, what bonds are forming. What experience do I have with this kind of thing? And when I start looking at the bonds that are breaking and the bonds that are forming, that's where I'm like, I just don't know. Without a table of bond energies, which wouldn't be accurate for this case anyway, I just don't know how many bonds are breaking and how many bonds are forming. If I started going through all of the like bookkeeping to try and keep track of like 2 HCl covalent bonds, 2 K plus to SO3, 2 minus ionic bonds, SO3 covalent bonds breaking, right? All of those ionic and covalent bonds breaking versus the ones coming back together. If I can't keep track of it in my head as like, oh, that's definitely going to be exothermic, endothermic, I'm just going to say I don't know, right? And so I look at that and I'm like, I have a hunch, but I really don't know. And in this case, I wouldn't trust my hunch.
Did you determine the delta S from this?
Ooh, great question. Can we determine it? The problem did not ask this, but delta H, I can't tell. Delta S, there's nothing in the problem that asks us to do at delta S, but can we say anything about delta S?
Yes, because there's a gas for it.
There's a gas being produced, so I have, again, there's that hunch like, oh, I think that's going to mean increase in entropy. Also, though, we have to keep in mind, we've got ions in aqueous solution, ions in aqueous solution, ions in, well, like HCl, aqueous, ions in aqueous solutions. If it was just like the solid dissolving, I couldn't tell because we've got that competition between the solid breaking apart and the waters kind of surrounding it. And so I've got a similar number of ions in aqueous solution. The fact that I'm producing some liquid will be maybe decreasing that entropy a little bit because of the way that the H and the SO3s are interacting with each other. But gas is usually a pretty big increase. So I would say S is right. I would say it's probably positive. Even in this case, like I would not put a question like this for predicting entropy on the exam because it's ambiguous. I like doing ambiguous questions in class and in office hours to kind of, I'm going to use that term, to show the ceiling problem, right? The most difficult thing we could do. And usually when we're trying to do the most difficult problems in this class, we're like, oh, we actually can't tell. We can talk through it, but we can't get to like, that's the answer. But we can show how we talk through it. So seeing the gas being produced makes me think that we're probably going to be a positive, right? Seeing how the solvation shell is changing around these compounds to be a water molecule, that makes me think that it might not be as positive as we would guess beforehand. But the fact that we're producing the gas, I still think it's going to be positive. Definitely ambiguous would not be on the exam, but interesting to think about.
Would something like this, but finding for delta H beyond the exam?
That's a little more definitive, but still kind of ambiguous in my opinion. I would do delta H and delta S problems kind of more in the context of things we did where we saw like good predictions.
Like knowing if it would be
The
positive
lattice,
or
the
negative.
hydration, the like the mixing, those things where we're like, oh, those have good trends. We can make sense of those. This where it's like we can kind of talk about it, but we can't say definitively. Maybe a free response question where I just want you to show how you think about it. And it's like, as long as you're thinking about it reasonably, you get points. Because I do free response questions like that, where it's like, give an explanation. The validity of your explanation is less important than the process of your explanation, if that makes sense.
Yeah.
So that's number 11. Lots of question marks. Pretty quirky. Did that help or did it confuse more?
No,
Good?
no.
Okay. So that brings us to 3.2 problems. Let's start with the mysterious number 3, which may or may not be our number 3.
It's kind of the same as the last one, but
That's great. Good bridging problem.
Okay, it's THCl4 solid breaks down into TH4 plus aqueous plus 4Cl minus aqueous, and it's asking for the sign of delta S.
Let's go ahead and do delta H while we're at it as well. Let's do all 3. What a quirky problem. I don't think this is not our number 3, is it? It's a great problem to do then. So definitely talk to people in other classes and get these ideas. So this is thorium tetrachloride. It's a weird compound. And we want to look at it and we want to say, okay, as it's breaking apart into solution, what can we say about delta S? I'm going to throw in what can we say about delta H, what can we say about delta G? And I'm pretty sure it's going to be like we can't tell. But the question becomes why? Can we explain why we can't tell? We're going to do our thinking for delta. Let's do delta S first because that's kind of what the question is actually about. When we look at delta S, whenever we're looking at a solid dissolving, we can think about it in terms of its 2 major steps. Right, delta S of lattice plus delta S of hydration. Right, we can think about it from the solid to the, let's do it this way. So the energy diagram we would think about is thorium Cl4 solid goes to thorium 4 plus gas plus 4Cl4 minus gas. And then when we surround it with water, I'm going to put a little dotted line because I don't know where it ends up, but that's going to be the process of going to thorium 4 plus aqueous plus 4Cl minus aqueous. Breaking apart the lattice, taking a rigid crystal structure and letting it jumble around as a gas is always a big increase in entropy. Taking those gas particles and surrounding them with water molecules is always a decrease in entropy. I know it's always an increase, always a decrease. Which one's bigger? We can't tell. We can't tell. This hydration thing, we can say relates to charge density. But relating to charge density doesn't allow us to say something about thorium tetrachloride. It would let me say something about thorium tetrachloride versus like some other compound. It would let me compare to other compounds. Like the one with the bigger charge density is going to have the bigger hydration energy, or the bigger decrease in entropy. Right? So it would let me say this hydration step, which one's bigger? But it doesn't let me say anything about thorium tetrachloride by itself. Because I don't know if I should have stopped the dotted line there or if I should have kept going. So I don't know how big this dotted line is supposed to be. I know it relates to charge density, but without any specific numbers, can't tell. We're going to have the exact same thing happen with the delta H. Right, so if we did this for delta H, we're going to have the same. The delta H becomes an even bigger problem. Because the delta H, this process of going up and this process of coming down both relate to charge density. Which means it's not even great for comparing because they're both going to change with charge density. This is if we were looking at delta H. Right. So I know it's going to be delta H of the lattice, delta H of the hydration. I know that's going to be the two steps I'm looking at. But now both change with charge density, and so they're going to be competing against each other. I can say even less about the delta H. So for these ionic solids dissolving in water, we really can't say much about delta H or delta S. This is part of why when we started doing this, as soon as we started talking about ionic solids, we went, let's just do an experiment. Right? Let's just measure what delta H is with a thermometer because we can't really predict it. But we can experimentally get at it really easily. So we can get this delta H as exothermic or endothermic really easily experimentally. Conceptually, it's difficult though.
Thank you.
Good? Okay. This one I can't really say anything about delta G. Right? If I don't know delta H, I don't know delta S, and I don't know the solubility rules for thorium tetrachloride. Now, chloride compounds are usually soluble in water, so I think delta G is going to be negative, but thorium is a weird compound, so it might not be. Can't say anything about delta G either. I did an example like this in my class where we did it for, I think we did it for like potassium nitrate. But nitrate compounds are always soluble, so even though we didn't know delta H or delta S, we knew delta G was negative.
Oh, right.
Because soluble compounds are going to dissolve.
Yeah. Nice.
Okay, so that's 3.2, number 3. Questions? Okay. Let's do number 7 next. We'll just go in number order.
Seven is the spontaneous versus product favor where you have to check all that apply.
Ooh, okay, so what's it say? Can you read the problem?
So like read all the following statements, like all that are true. So the first one's for a spontaneous process, the delta G system is greater than 0. But it's like the one with the little circle on it.
Standard, okay.
Standard, okay. The second one is for a spontaneous process, delta G system is less than 0. But that one's without the circle.
Oh, wow, okay. See ya.
Thank you.
Third one's a process that favors products at equilibrium has the delta G system equal to 0.
Oh, wait, read that sentence again very carefully.
A process that favors products at equilibrium has delta G system equal to 0.
Interesting.
That one's without the standard.
Okay.
The next one is a process that favors product at equilibrium has delta G standard system greater than 0.
Is it greater than 0?
Yeah. The fifth one, a process that favors products at equilibrium has the standard delta G system equal to 0. Next one, for a spontaneous process, delta G system is greater than 0.
Okay, delta G standard?
No, just the delta G.
Greater than 0.
Yeah, our system, yeah. And then the next one, it's the same one, but it's the standard delta G system. And then there's 3 more.
Oh my goodness.
It says a process that favors products at equilibrium has the delta G system greater than 0.
The delta G
Just the delta G one.
greater than 0?
Yeah. And then a process that favors products at equilibrium has delta G system less than 0. And the last one, a process that favors products at equilibrium has the standard delta G system less than 0.
Oh, I got one of these wrong. Was the second one equal to 0? Second to last?
Second to last? No, it says less than 0.
What was the last one?
Standard delta G is
Standard. Okay, scrunched in the last one at the bottom. Right, so this is, what are we supposed to do with all of this, right? So, we are going to be making a bigger distinction between the system, the standard, and the non-standard, and kind of looking at how we deal with this. This is like kind of like a textbook reading problem, right? We haven't talked about this in class that much. We've been using kind of spontaneous and product favored kind of interchangeably, but they actually do have different definitions. When we're talking about spontaneous, non-spontaneous, and I'll be curious to see how this problem goes. So this is, like I mentioned, a kind of a textbook problem where it's using very particular definitions for where do we talk about things being spontaneous versus where do we talk about things being product favored as we approach equilibrium. We haven't had like this phrase at equilibrium also got me for a second because I was like, oh, do you mean when it's at equilibrium it has more products? Or do you mean the process as it approaches equilibrium? I'm gonna tell you which ones are the right answers, and I'm gonna do a graphic. I'm gonna do like a little plot that we're doing today in class that will hopefully help make the distinctions between these. Fundamentally, those delta G standards, we use the standards when we're talking about product favored versus reactant favored. We don't use that standard when we're talking about the word spontaneous. So where I've got the delta G standards and spontaneous, I don't want to do those. Same thing when we're talking about product favored. I want to be using the standard versions, so I don't want to use that one. I don't want to use any of these ones on the bottom, right? Well, this last one I can, but that one and that one I don't want to use. So if I'm talking about product favored, I want to be looking from standard conditions. If I'm talking about product favored, I want standard conditions. Spontaneous, I want to be talking about any conditions. Because spontaneous can mean a lot of different things because non-standard conditions can mean a lot of different places. So when we look at product favored, okay, now we can say those ones we wouldn't consider. Again, this is by the definition, the way the textbook talks about it as well. So which ones are true? If I'm going to be spontaneous, I want my delta G to be negative. So that's going to be that one. And if I want to be product favored, I want my delta G to be negative. My delta G standard to be negative. That would be the last one. And so those should be the only two that we actually select. Now, does that make some amount of sense?
Yeah.
Let me show you the thing we're doing in class. I want to practice it for class today as well. I think every office hours in the last 2 weeks I've been like, I'm going to practice this for class. It's always a good idea to get ahead. It's good to see things twice. It's good to see things before you see them in class for the first time. So let's look at a Gibbs plot, which is a pretty weird plot, but I think helps make sense of this problem really nicely. You ready? After writing all of that down, that's all the time it took. So, a Gibbs plot goes like this. We've got this thing. We're going to plot Gibbs free energy on the y-axis. Not delta G, just Gibbs free energy. And we're going to plot this thing called Q along the x-axis. This is the reaction quotient. This is a ratio of products to reactants. It essentially allows us to track how far through the reaction are we. In all of our classes, we start with a Q of 0. No products, all reactants. And then as we go forward, we get to a point where our products and reactants are equal to each other. And then it keeps going, and we eventually get to a point where we've got no reactants, all products. We actually go all the way up to a value of infinity. Right? We can get to a Q value of infinity. That's when, actually impossible, but like that's where all of the reactants disappear and we only have products. So when we look at this, we can say, okay, how does a reaction proceed to get from one side towards the other? And it turns out that there's going to be an energy saddle. There's going to be a spot where the reaction stops because the enthalpy and the entropy kind of run out. And so we end up making curves. I'm going to make, if we had our 124 problems, they look like this. Oh, that's not how you spell like it at all. Whoa, what is going on with my writing? Trying to lean too far. Right, so in Chem 124, we saw reactions like this, where there's a little, like there's a spot almost at infinity, right? The reactions just go to completion. They make all products, reactants, one of the reactants goes to 0, so if I took my ratio of products to reactants, I'd have a number over 0, I'd get infinity. That's not what really happens when we take energy into account. And this is the first time we've been actually able to explore that, because we now understand delta H and delta S, which will make it so we don't go all that way. If we wanted to, our delta G would be from non-standard. Our delta G would be from any point to any other point. That would be a delta G. Or from this point all the way down to, all the way down to that point, that would be a different delta G. Right, and we could make hundreds of different delta G's because we could just do the difference between two things. And as long as it's like going a downward slope, it's spontaneous. Standard is specifically from 1 down to the bottom. That is delta G standard. And so in this case, my delta G standard is going to be going towards more products, right? My Q is going to be getting bigger to get to standard. So that's where I say my standard condition from 1 is going to be product favored as I approach equilibrium. Now, this is just one possible graph. We have technically an infinite number of these because the curves can look different ways. Let me just show you at least one other. Right? Another curve we could draw, right? This could be different temperatures. Most likely is a different chemical reaction. One where there's actually, it doesn't go all the way to infinity, which we haven't been able to do before now. So this is going to be a different type of problem, a different type of chemical reaction. I might have something. Do you want it to be product favored or reactant favored?
We could do reactant favored.
Let's do a reactant favored one. This is going to be kind of quirky. So in that case, how do you think it's going to look if we do reactant favored?
Probably like the curve and then straight.
Yeah. So if we do reactant favored, we're going to have our saddle point, the lowest point on this Gibbs energy curve, is going to be before 1. So now if I did my delta G standard, I would come from there That would be my delta G standard. And notice, it's going to go towards reactants from standard conditions. If I started over here at 0, right, which is what we do in most of our chemical reactions, if I start here at 0, I still have to go, my delta G would still be making, my Q would be increasing. I'd be making more products if I started at 0. This would be a spontaneous process to make some products, but my reactants would not go all the way to 0 like we saw in 124. My reactants would only use up a small amount when the reaction stops going. Why does the reaction stop going? Delta H, delta S. The enthalpies and the entropies kind of stop the reaction from happening as much as we've seen before. New thing we haven't really talked about. Reactions don't just go to completion. They have what we call an extent of reaction. How much does it go before it stops? Could we force it to keep going? If we could have some way to push energy in, we could, but it would be non-spontaneous because I would have to go up this energetic curve. I'd have to put energy in to make it happen. It would be a non-spontaneous process to get it to make more products. Should I do one that's product favored? Or do you guys kind of see the pattern?
I see the pattern.
One more?
Yes, please.
One more?
Yeah.
Okay, let's do one more. So then we can add, and again, we can draw hundreds of these. Then we can do one more for our 3 main cases we look at, in my opinion. Right? So this one has a saddle point. The saddle point isn't all the way at infinity. It's not even close to infinity, but it's past 1. Right? So in this situation, my delta G standard is going to, ooh, that's a really short delta G standard. Let me make that a little bit different. I want to give myself a little bit more space to write. So I'm going to do this. Let me look at it straight on so I can make this right. All of my lines are crooked. There, I like that a little bit better. So my delta G standard in this case would be from where this curve is at 1 all the way down to the bottom. That would be my delta G standard. Right, from this G to that G would be my delta G. My first point is at the standard condition, and then all the way down. So that would be, as I approach equilibrium, I would be going to more products, my Q would be getting bigger. And since my Q has products on top, that's going to be more products. Again, at this point, I can draw hundreds of different delta Gs. I could make delta Gs that are non-spontaneous. I could make delta Gs that are spontaneous. If I wanted at any point to go from here up to there, I wanted to go up that curve, that would be a non-spontaneous process. However, if I made a lot of products, like if instead of going that way, if I started here, where I mixed a bunch of products together, I could end up going backwards the other direction to make more reactants in that process. There's such a thing as too many products. It's raining. So there is such a thing as in these graphs, there's such a thing as too many products. In this graph, like the one we've been using most of chemistry, there's no such thing as too much products. This graph, there's such a thing as too much products. I can make another delta G, right? I could do a delta G that's just right there. Since that's going down the curve, that would be spontaneous. If I tried to do that delta G up the curve, that would be non-spontaneous. So delta G, I can write hundreds and hundreds of delta Gs on one graph. There's only one delta G standard, though. That's from the 1 to the bottom of the curve. That bottom of the curve gets a special label. Instead of just calling it Q, we give it a special label. We call it KEQ. It's the equilibrium point. It's the balance point between products and reactants. We'll be doing this in class today. Is it 2? Okay. Questions?
I said
We didn't-
one question.
We didn't get to 10 and 14.
Yeah.
Thank you.
You bet, see ya.
Are you able to help me on that one?
Yeah, was it 10 or 14?
10.
Let's do 10 real quick. I'm going to erase this. We're going to do 10 real quick. Did you have a quick question while I'm erasing?
Yeah, it's just about this one. If it says at equilibrium, does that just, if it's product favor at equilibrium, it just means when that reaction is done and like the concentrations
Yes.
are,
Right.
now they're equal. It's that it made more products.
To reach equilibrium,
Oh, okay.
right?
But that doesn't affect, like, it's not that if you're saying that it's product favor at equilibrium, it should be, delta G should be less than 0. It's just telling you.
Well, so if we are talking delta G, at equilibrium would be 0. But if we're talking delta G standard, it's going to go from standard conditions to equilibrium.
Right, so if you're saying it's, like, delta G is product favor at equilibrium.
That would be a weird thing to say. You'd have to say delta G standard.
Okay.
Yeah.
Thank you.
Okay, so we're doing number 10?
Yeah.
Okay.
It was for the process shown, using no other resources, give the sign positive, negative, 0 are unknown for delta S system, delta S surroundings, delta S.
Okay, what's the process?
I just want to
Here, this is the,
Okay, so we got, oh yeah, this one's fun. H2O liquid going to H2O gas at 1 atmosphere. And we'll take this one.
Okay.
That's her turn. And 80 degrees Celsius. Okay. And we're doing a bunch of delta S things.
yeah.
So the delta S's are interesting. First off, does water boil at 80 degrees Celsius?
No.
No. So we can do the delta G pretty easily. Delta G is going to be greater than 0.
Oh, that makes sense.
Right.
I just like don't know how to like approach these problems.
Yeah,
and
so we're
think
going to do
about
what I
it.
think are the two easy ones first. Right, water doesn't boil at 80 degrees Celsius. We know that. Right, you could argue that it's like, oh, do we know that? Because it says only given in the problem. It's assuming we have some knowledge. Right, if we were literally just doing what was given in the problem, we're like, well, I only know that it's at 80 degrees Celsius. I have to pretend like I know nothing about water. And then it'd be an impossible problem, right? It's assuming we know water boils at 100 degrees Celsius. Water doesn't boil at 80 degrees Celsius. At 1 atmosphere. If we change the pressure, maybe. The other thing that we can do, and that is delta G. Right? The other thing we can do is delta H. Does it take energy to boil water?
Yeah.
Because we're breaking IMF. So delta H is going to be endothermic. Right? We know those two for sure. The ones that are a little bit weird are the entropy terms. And this is, again, a textbook problem in my opinion, because we didn't spend a lot of time talking about delta S of universe, delta S of surroundings, and delta S of system.
Well, isn't delta S of the universe always positive?
Yes.
Okay.
And we spent most of our time talking about delta S of system. All the delta S's, delta H's, and delta G's we talked about in class were for the system. So, if we're going from liquid to gas?
It's increasing entropy.
Yep. So, that has to be greater than 0. Now, if delta S of system is greater than 0, these things, can we say anything about delta S of the surroundings then?
Would it be unknown? Would that one be the unknown?
I think so. I'm having trouble remembering now. There's something about how these two things relate to each other, but if both of these are positive, the delta S surrounding could be a little bit positive or a little bit negative, right? The delta S surroundings, I'm not sure.
Okay.
And I think that's...
It said it was negative.
Oh, it's negative?
Oh,
Okay.
it is.
So, it turns out, okay, so here, that's where I was like, I think there's a rule in the way that these two things relate to each other, where if the delta S of the system is increasing, the delta S of the surroundings has to be decreasing, but it has to be decreasing less than this increases. So like these two things relate to each other. It's kind of like these two things relate to kind of like Q in and Q out.
Yeah.
Where they have to be like opposites of each other, but for entropy they don't have to be equal.
Okay.
And so that's kind of that weird quirk. Again, this delta S surrounding delta S universe.
Yeah.
Don't worry about it too much for this class.
Okay. Is like something like this gonna be on the midterm thing?
Universe surrounding? No.
Okay, it's just gonna be like G,
Systems.
H, and S. Got it.
Yeah,
Okay.
systems. Systems
That
is what
makes
I'm worried
sense.
about. Okay. I'm gonna stop recording.